Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. In this session, we are going to learn about heat capacity. Okay. In thermodynamics chapter, we are speaking about the heat capacity. So, what is meant by heat capacity? So, heat capacity of a substance is the amount of heat required to raise the temperature of a substance or a system through 1 degrees. 1 degree means 1 Kelvin or 1 degree centigrade. So heat capacity of a substance is the amount of heat required to raise its temperature. For example, let us take a system. This is a substance or a system. Okay. We are taking some gas in a cylinder, system or a substance. Any substance we can consider. So initial temperature is something like 25 degrees centigrade. 25 degrees centigrade. To raise its temperature through 1 degree centigrade. So to raise its temperature to 26 degrees centigrade, how much amount of heat is required? How much amount of heat is absorbed, or how much amount of heat is required to raise its temperature through 1 degree centigrade or 1 Kelvin, and that is called as what? The heat capacity. So heat capacity, mathematically, how can you represent it? Heat capacity is the ratio of heat absorbed by the system. See here, Q is heat absorbed resulting, it is the ratio of heat absorbed by a system to the resulting increase in the temperature. So mathematically, how can you represent C is equal to, so C is the symbol to represent heat capacity. Heat capacity is represented by capital C. So C is equal to Q by dt. So Q is the amount of heat absorbed by the system, and dt, for example, what is dt? dt is infinite small change in temperature. Change in temperature. Infinite small change in temperature. dt. When you consider delta T, what is finite change in temperature? Finite change in temperature. So that's the difference between dt and delta T. Okay. So heat absorbed, Q is heat absorbed by the system, and dt is rise in temperature. So infinite small rise in temperature, right? So what will be the units? C is equal to Q by dt. In SI unit, see what is the unit to calculate heat? Joule. So units joule per Kelvin. Joule per Kelvin. Change in temperature is measured in kelvins. Then heat capacity at constant volume. We are taking at constant volume. Gives the measure of change in internal energy of the system with temperature. Okay, heat capacity at constant volume. So heat capacity, it is the amount of heat energy required to raise the temperature of this whole substance or whole system. So whether the whole system contains 1 mole, 2 mole, half mole, 25 mole, it doesn't matter. So heat capacity is calculated for the whole system taken, whole substance taken. Now we are speaking about molar heat capacity. Molar heat capacity. So molar heat capacity means Cm. Cm. So here M represents that it is molar. So molar heat capacities are two types. One is molar heat capacity at constant volume, molar heat capacity at constant pressure. So generally we don't mention M, simply we say that it is CV. Very clearly speaking about CVM, that means molar heat capacity at a constant volume. At constant volume. Molar heat capacity at constant volume. CV, CP, CPM. Is that CPM represents that molar heat capacity at constant pressure. At constant pressure. Right? So here for 1 mole we are discussing. Before, heat capacity means how much amount of the substance, whatever the amount of the substance it is taken to increase the temperature of that whole substance, how much amount of heat energy required is called as heat capacity. But whereas here molar heat capacity means it's calculated for 1 mole of the substance. It's always calculated for 1 mole of the substance, and CV means here at constant volume and CP means at constant pressure. Okay. So let us see here. CV already mentioned here. So CV is equal to, so molar heat capacity, M is not mentioned, or you can also mention it. CV is equal to, so Q by dt, when the change or rise in the temperature is infinite small, we use dt, Q. And this heat is absorbed at constant volume, so we mention it as QV. And if we know, in the previous videos we have seen that, or in the previous lectures we have seen that delta U is equal to QV for finite change. For infinite change also du can also be written as QV. So then I can write it as QV is equal to delta U or du by dt. So this is all for infinite small change or infinite small increase. So this can be mentioned as du by dt at constant volume. This can also be mentioned in this way. So this V represents that it is at constant volume. So for finite change, I can mention that CVM, molar heat capacity at constant volume, is equal to QV by delta T. This is for finite change. So I can write it as delta U by delta T. Now from this equation, I can also write it as delta U is equal to CV into delta T. I'm not mentioning M here. You have to remember that it is molar, and this is for 1 mole. For n moles, delta U is equal to n into CV delta T for n number of moles. So then what will be the units for CV? So units for CV, molar heat capacity is joule per 1 mole, no, mole per Kelvin, joule per mole per Kelvin. Okay, so delta U is equal to NCV delta T. You need to remember this formula. Based on this, we are asked questions in JEE main. whatever the competitive examination we write. Now we are speaking about CPM. So CPM, that is molar heat capacity at constant pressure, is given by Q by again dt for infinite small increase in temperature. As the process is happening at constant pressure, we can write it as Qp by dt. In the previous lectures, we have studied that Qp is equal to delta H for finite change. For infinite small change, Qp is equal to dH. Infinite small change. Then what I can write here, this can also be written as dH by dt. This can also be written as dH by dt at constant pressure. Okay. So for finite change, then I can write it as Cp. M I am not mentioned, so otherwise write as Cpm is equal to delta H by delta T. So from this I can write it as delta H is equal to Cp into delta T. Okay, Cp into delta T. So this is for 1 mole. For n moles, delta H is equal to n into Cp delta T for n number of moles. So delta H is equal to n into Cp delta T. This formula we need to remember. And delta U is equal to n into Cv delta T for finite change. Okay. So that is about heat capacity, molar heat capacity. And for this also units you can write Cp units is equal to joule per, it is also per mole. So mole into Kelvin, joule per mole per Kelvin. Next, coming to specific heat capacity, specific heat. In other words, it is also called as what? Specific heat. So specific heat represented by small c. So it is the quantity of heat required to raise the temperature of 1 gram. See here, 1 gram. This is important. 1 gram of the substance through same 1 degree centigrade or 1 Kelvin. When we are speaking about molar heat capacity calculated per 1 mole. Here heat capacity calculated for 1 gram. 1 gram, right? And we know that 1 mole is equal to molar mass of a substance. Molar mass, in 1 mole there will be 1 molar mass or gram molecular weight of a substance. So heat capacity or this is molar heat capacity. What is this? This is molar heat capacity. It is calculated for 1 mole of the substance. If you want to know for 1 gram, then you have to divide with the molar mass. What you need to divide with the molar mass. If you divide it with the molar mass, then you can get for 1 gram. So heat capacity, let us represent it as C, heat capacity C, molar heat capacity. So by molar mass gives you specific heat capacity. Specific heat capacity is represented by small c. So specific heat capacity is equal to specific heat capacity. Capital C represents specific small c represents that it is a specific heat capacity, small c, capital C by molar mass. So capital C is molar heat capacity, molar heat capacity. So molar heat capacity is calculated for 1 mole. If you divide with the molar mass of a particular substance, then what do you get? Specific heat capacity. So this is the specific heat capacity. Capital C is molar heat capacity. So mathematically, how can you represent it? C is equal to Q, heat amount required to raise 1 gram of a substance through 1 degree centigrade. Or C is equal to M into C delta T. So what will be the units? So units of specific heat capacity. Q means joule by M gram into delta T Kelvin. So these are the units for specific heat capacity. Right? Next, let us see relation between heat capacity and specific heat capacity. So molar heat capacity, for example, let us take molar heat capacity C Pm is equal to specific heat capacity at constant pressure into molar mass. Molar heat capacity at constant volume is equal to specific heat capacity into molar mass. Okay. Molar heat capacity at constant pressure is equal to specific heat capacity at constant pressure into molar mass. Molar heat capacity at constant volume is equal to specific heat capacity at constant volume into molar mass. Okay, so that will be the relation between these molar heat capacity and specific heat capacity. Right? Next, coming to let us see the relation between Cp and Cv. Relation between Cp and Cv. Cp and Cv. So molar heat capacity at constant pressure and molar heat capacity at constant volume. Right? Already we have studied that we have a formula. What is that? H is equal to U plus PV. H is equal to U plus PV. Then for ideal gas, already we know that PV is equal to nRT. So instead of PV, you can also write nRT. So H is equal to U plus nRT can also be written. Okay. Then delta H is equal to delta U plus delta nRT. Okay. So delta H is equal to delta U plus delta nRT plus nR delta T. Okay, R is constant. And when you are doing an experiment with a specific number of moles, let us see here we are taking number of moles constant. In this gas, okay, N is constant. You are not adding mass, you are not adding gas, or we are not removing gas, right? N is equal to constant. Delta N is equal to 0. N is equal to constant, automatically delta n will become equal to 0. Then delta H is equal to what you can write, delta U plus delta nRT, 0 into RT plus nR delta T, nR delta T. Then what do you get? So delta H is equal to delta U plus nR delta T. Delta H, already we know that delta H is in the previous page we have studied that N C P delta T is equal to N CV delta T plus N R delta T. You can take N delta T as common, Cp is equal to N delta T common, Cv plus R. N delta T you can cancel it. So Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Right? So this is the relation between Cp and Cv, which is equal to universal gas constant. So what is Cp? Actually, clearly speaking, Cpm, molar heat capacity at constant pressure, minus Cvm, molar heat capacity at constant volume, is equal to R. Okay. So in the previous page we have seen that now Cpm minus Cvm is equal to R. If you derive the relation between molar heat capacity at constant pressure and specific heat, so specific heat, molar heat capacity is equal to specific heat into molar mass, specific heat into molar mass, minus molar heat capacity is equal to specific heat capacity into molar mass is equal to R. If you take molar mass common, specific heat at constant pressure minus specific heat at constant volume is equal to R. Specific heat at constant pressure minus specific heat at constant volume is equal to R by M. So this is the relation between the two specific heats, and this is the relation between two molar heat capacities. Okay, Cp minus Cv is equal to R. Here Cp minus Cv is equal to R by M. What are the Cp and Cv? This Cp and Cv are specific heat capacities at constant pressure and constant volume. These two are molar heat capacities at constant pressure and constant volume. Okay. And we do have a ratio, and that ratio is called as Cp by Cv. Molar heat capacity at constant pressure by molar heat capacity at constant volume is given by gamma. What is gamma? So we will study what is gamma. Simply mathematically representing the ratio of the two specific, the ratio of two heat capacities is given by gamma. So which is also called as Poisson's ratio. Poisson's ratio. Okay. So Cp minus Cv is equal to R, and Cp by Cv is equal to gamma. These two we need to remove, right? So next, coming to here, for different gases, what are the values of U, Cv, Cp, gamma? So first one, let us take it a monoatomic gas. Monoatomic gas. So for monoatomic gas, the degrees of freedom to move. So here, what is this degree of freedom? Degrees of freedom. Degrees of freedom means the axis in which simply understanding, you don't have degrees of freedom in this chapter. So degrees of freedom, for example, this is x-axis, y-axis, z-axis. Monoatomic gas, this monoatomic gas can move in this direction and in this direction. So its degrees of freedom are 3. Likewise, diatomic and polyatomic linear gases. Diatomic and polyatomic linear gases. So for example, O2, linear gas. Its degree of freedom is 5. Okay. Along with linear motion, it can also rotate. Due to that, its degree of freedom will be 5. Polyatomic gas, which are non-linear, different shapes, the degree of freedom is 6. So simply, in chemistry, we have only introduction about degrees of freedom. We don't have details regarding the degrees of freedom. We need to remember, for monoatomic gas, the degrees of freedom is 3. For diatomic gas and polyatomic gas, which are linear, degrees of freedom are 5. And for polyatomic gases, which is non-linear, the degrees of freedom is 6. And internal energy is given by the formula. What is that? N by 2 FRT, or simply speaking, F by 2 nRT. F by 2 nRT. So if you consider 1 mole N is equal to 1, then U will be equal to, degrees of freedom is 3. So 3 by 2 RT for monoatomic gas. Which gas? Monoatomic gas. For diatomic and polyatomic gas, which are linear in shape, then we get 5 by 2 RT. Is that a diatomic gas? The same way, U is equal to F by 2. For polyatomic, 6 by 2 RT. So polyatomic. So what is U? We know that it is internal energy. It is internal energy. And CV. CV is given by formula F by 2 R. F by 2 R. And Cp is given by formula F by 2 plus 1 into R. So for monoatomic gas, let us take Cv is equal to 3 by 2 R. Cp is equal to 3 by 2 plus 1 R, which will be equal to 5 by 2 R. Right? In the same way, diatomic gas. For diatomic gas, Cv is equal to 5 by 2 R. Cp is equal to 5 by 2 plus 1 R, which is equal to 7 by 2 R. For polyatomic and non-linear molecules, Cv is equal to 6 by 2 R, which is equal to 3 R. Cp is equal to 4. Okay. And we studied that gamma is equal to Cp by Cv. Gamma is equal to what? Cp by Cv. For monoatomic gas, gamma is equal to, what is Cp? 5 by 2 R by 3 by 2 R. So what do you get? 5 by 3, which is equal to 1.66. For diatomic gas, gamma is equal to 7 by 2 R by 5 by 2 R, which is equal to 7 by 5, 1.4. For polyatomic gas, which is non-linear, or for triatomic gas also, we can triatomic gas also considered to be polyatomic gas. So 4R by 3R, which is equal to 4 by 3, 1.3, right? So this is how to calculate gamma, how to calculate Cp, Cv, and how to calculate U, right? Then let us go with so that is concepts regarding heat capacity. Thanks for watching up to the end of the video. If you like the video, like, share and subscribe the video. Subscribe to the channel. In the next session, we shall solve some PYQ on heat capacity. Thank you.